You know that simple Pez dispenser? Ever really thought about how it works? It's so simple, so intuitive, but that exact same idea is actually one of the most important building blocks in all of computer science. Yeah, this quote from a classic textbook just hits the nail on the head. You load the candies in from the top, and when you want one, you can only get the very last one you put in. It's a perfect, real-world example of what we call a stack. So, okay, a candy dispenser. What in the world could that possibly have to do with your web browser's back button? It sounds kind of random, right? But believe it or not, they are built on the exact same, really elegant principle. And that principle is called LIFO, last in, first out. It's exactly what it sounds like. The last thing you put in is the first thing you can take out, just like that Pez candy. This one single rule is what defines a stack. Okay, so we've got the basic idea. Now let's get a little more formal. Let's see how computer scientists lay out the official rules of the game for a stack, using something called an abstract data type, or ADT for short. So what is an ADT? Well, think of it like a blueprint for a machine. It tells you what the machine is supposed to do, the buttons you can press and what they accomplish, but it says absolutely nothing about the gears and wires on the inside. It's all about the capabilities, not the mechanics. The first rule, our first operation, is push. When we push an element, we're just adding it to the top of the stack. This is our load the candy move. Simple as that. Next up is pop. Now this one does two things at once. It removes the top element from the stack and it hands that element back to you. This is the get the candy operation. But what if you just want to see which candy is next without actually taking it? Well, that's what the top operation is for. It lets you just peek at the top element, but it leaves the stack exactly as it was. We also need a couple of little helper methods. Size is as straightforward as it gets. It just tells you how many items are currently sitting in the stack. And isEmpty is our safety check. It's a simple yes or no question. Is there anything in the stack at all? This is super important because it stops us from making mistakes, like trying to pop from a stack that's already empty. So here they are, all in one place. Our 5 core methods: push, pop, top, size, and empty. This simple little set of rules is the complete definition of what a stack is and what it can do. Okay, so we have the abstract rules. But how do we take that idea and turn it into something a programmer can actually use? Well, in a language like Java, the answer is something called an interface. An interface in Java is basically a contract. It's a formal agreement that lists out the exact methods a class must have if it wants to be considered a stack. It's the bridge that takes us from an idea to actual working code. And would you look at that? This code shows the connection perfectly. See those method names? Size, empty, push, top, and pop? It's a direct one-to-one translation of the ADT operations we just talked about. This is the blueprint in action. So what makes this so powerful? Well, first, it's set non-negotiable contracts. And second, see that little X in there? That stands for generics, which is a fancy way of saying our stack can hold any kind of object. A stack of numbers, a stack of names, a stack of whatever you want. It's incredibly flexible. All right, we've talked about the what, the rules, and the blueprint. Now it's time to finally look under the hood and see the how. We're going to build a working stack using one of the most basic things in programming, a simple array. And to build this machine, we only need 2 parts. That's that simple. First, an array, which is going to be the container for our stuff. And second, just a single number, which we'll call t, that acts as a pointer to always keep track of where the top of the stack is. So when our stack is brand new, the array is empty, and we set our top index t to -1. Now, since array spots start at 0, setting t to -1 is a really clever way to signal that the stack is totally empty. There's no top element yet. Now, to push an element, it's a quick little 2-step. First, we increase t by 1, so if it was -1, it becomes 0. Then we just place our new element into the array at that new spot. And that's it. We've just added an item to the top of our stack. And popping is just as simple, but in reverse. First, we grab the element that's sitting at our current top index, array sub t. Then we just decrease t by 1. See? We don't even have to erase the old data. Just by moving the index back, that slot is now considered empty. Finally, we return the element we grabbed in step 1. This array-based stack is beautiful. It's so simple, and it is incredibly fast. Push and pop are lightning quick. But there's always a catch, isn't there? The downside is that arrays have a fixed size. If you try to push onto a full stack, you'll get a stack overflow error. So it's a classic choice between pure speed and flexibility. And now we can finally answer that first question. Your browser's back button is a stack. Every time you visit a new website, its address is pushed onto the history stack. When you hit the back button, the last site is popped off. The same last-in, first-out principle is what powers the undo feature in software, and even manages how functions are called deep inside the computer. So really, the stack is just perfect proof that the most powerful tools are often built on the simplest rules. That one single principle, last in, first out, gives us solutions to so many complex problems. It really makes you wonder, right? Where else do we see such amazing, complex things grow from such simple beginnings?